Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. This time we're going to be talking about colliding and interacting galaxies. Last time we were looking at the Hubble classification of galaxies and saw that many of them look distorted or messed up in some way, and those are the peculiar galaxies. We also indicated that possibly galaxies are forming by collisions and mergers. So now we're going to see how that actually works. All right, so the first step to think about is that galaxies fill the space around them, unlike stars inside of galaxies, because remember, galaxies are made up of stars, hundreds of billions of stars, such as these two examples that we see here. The examples that we see below have a huge number of stars in them. Though the fuzziness of a galaxy isn't because it is gassy, well, it is very gassy, but it's because of the collected illuminated light of all the hundreds of billions of stars within them. But the stars themselves don't touch. They're separated by roughly 10 million times their sizes. So stars are incredibly far apart compared to their sizes. However, galaxies, which are assemblages of stars, are actually separated by roughly only about 20 times their diameter. The Milky Way and Andromeda galaxies are roughly about 100,000 light years across and are separated by 2 or 3 million light years. So therefore, their distance between is only about 20 times their diameter. So that means galaxies are very likely to encounter each other and collide, unlike the stars that make them up. All right, so the way we will indicate that we understand how things are going are by tidal interactions. And so all interactions that galaxies do, it's not the electromagnetic force or the weak nuclear force or the strong nuclear force or I don't know, Sailor Moon force or something. You can make it up, but they interact via their gravitational pull between each other. They're extraordinarily large, and because of that, the near side gets pulled on by more than the far side, and so they get stretched out. So the tides distort the shape of the galaxy. When we say tides, what we really mean is the differential gravitational pull, or the difference in gravity pull between one object and another compared to their center of mass. So peculiar galaxies occur in interacting pairs. That's very frequently what we see. And so here's that image again. We see the two spiral galaxies interacting, and there's another pair of spirals from the Hercules cluster of galaxies. And this is what we might think of as a high tide. Notice that the Whirlpool galaxy seems to be elongated towards the elliptical with which it's having an encounter. So it's getting squished along the line of sight and stretched towards the line between them and stretched along the line between them. And in so doing, when there are interactions, you should expect to see massive amounts of star formation, which is what you do. See all those pink glows? That's because the gravitational pull between the shocks that are occurring because of the tidal interactions are causing the gas clouds to merge and collide and form stars rapidly. So you get tidal stretching along the line between the two of them. And that's what we see with the ARP-87 interacting galaxies. And when they're called, this group is called ARP because after Halton ARP, who is an amazing observer, and he found a whole bunch of very, very strange things. So if you look for the ARP catalog of galaxies, you're going to see all sorts of really interesting, peculiar galaxies. All right, so here's another peculiar galaxy called the Tadpole, which has an enormous tidal tail. And then we see the Mice, which also has an enormous tidal pair of tails as they're interacting. And notice you have a huge number of blue stars, and then you have these yellowish cores, which are in the process of merging. And here's another beautiful interacting pair as they swing around each other. These interactions take quite a long time. They'll take up to 1 billion years or so to fully complete. And it's important to remember that we see stars also. The stars have spikes, and the starry spikiness that we're going to see here, those are all foreground Milky Way stars. They are not distant. They are distant in the sense that they're tens to thousands of light years away. But the fuzzy clouds that look like the galaxies, those are millions of light years away, or tens of millions of light years away. And if you look very carefully at these images that I'm showing you, you'll find that there's actually little tiny galaxies far, far, far in the distance that are extraordinarily small, and they are much more distant galaxies, maybe 100 million light years away or greater. All right, here we go. So computer simulations show that they take about 1 billion years to conduct this dance of collision. So this is not a fast thing, even though they're traveling at hundreds of kilometers per second or up to thousands of kilometers per second. The sizes are so enormous at hundreds of thousands of light years across that it really does take billions of years for the interaction to occur. And so you take the simple rules of Newton's laws of motion, you take his law of gravity, you plug it into a computer, you then try to take into account other things, say dark matter, which we talked about with the Milky Way in the previous lecture. But if you take all those things into account, then you see the shapes occurring. So if you have taken into account all of the mass, all the underlying mass, and then look at tracking the individual particles, and you might call clusters of stars particles or big clouds of gas particles, and then if the models match the observations, then we know we're on the right track. Some number of them that occur that people have done. Dr. Dubinsky over at Canadian Institute of Theoretical Astrophysics has created a wonderful series of videos that you can go check out. There's his website. And there's others that occur as well, and direct galaxy collisions are really, really, really pronounced. When they occur, and when you have very, very tight collisions where the cores come very close to each other, there's a huge amount of what we call starburst activity. And starburst activity means the clouds of gas and dust collide and get overdense and form stars very, very, very rapidly. All right, so what they did with the whole group is that this set of images was used to kind of help guide that group of that simulation that we saw. So Summers took these images and rotated around, and basically this is what you get when you take a couple of spiral galaxies that are similarly sized and just slam them into each other from various angles. The disks of the galaxies get distorted, tidally disrupted, and all depends on the orientation that they come in at. So this is what they look like when you have two radically interacting galaxies. And we see that now that we have a good computer simulation that seems to be doing exactly what we see in nature, we think we're on the right track. So there's a good close-up of one of them showing the starburst activity in the ring formation, and another one that shows more star formation in both of the galaxies. And here's one that's showing incredible tidal disruption. Again, look at the tiny, tiny, tiny distant galaxies far, far away in the background. We can see that the blue stars are actually being stripped away from the center and actually sent out, way out and away from the tidal interaction. So the gas clouds had formed and the blue stars were essentially just left behind as they are forming. So we can see that the interaction is happening on the order of hundreds of millions or tens of millions of years, because those blue stars trace out a time frame of about 10 to 100 million years. Okay, here's another one we see where the intense star formation actually happening right in the center. And then finally, here's another gorgeous pair that show interaction and star formation all throughout it, with the hydrogen gas clouds going pink, the blue star clusters appearing all over the place. And we can tell that this is extremely distant because they're out of focus. Or more specifically, they're not resolved. And since they're not resolved into individual stars, those blue dots aren't individual stars, but huge groups of stars, many thousands or tens of thousands of blue-type stars being formed all at once. And here's ARP-273, sometimes called the Rose, which is an enormous, beautiful-looking interacting pair, and we can see that the Hubble Space Telescope image can certainly bring out the more interesting aspects to it. And this is the Stephan's Quintet, which is actually four interacting galaxies, and the bluish one is in the foreground. But the four interacting galaxies are certainly having an extreme interaction with respect to each other. And if we rotate around and look at this image from a slightly different angle, this is the Hubble Space Telescope image merged with the Chandra X-ray image. And if we go back and forth between the Chandra X-ray image and the optical plus X-ray image, we see that the hot X-ray gas is being created in that area where the stars are forming extraordinarily rapidly. So X-ray emitting gas is being heated to tens of millions of degrees as black holes and neutron stars are being formed in great rapidity there. So you can have ring-like encounters as well, and if a small galaxy goes smack through the middle of it and hits a bullseye, then you can create a circular wave of star formation, such as we see here. And this is a Hubble Space Telescope image that shows a very, very, very violent interaction between a little galaxy that literally went smack through the center. The little galaxy got completely disrupted, but it sent shock waves through the rest of it, which then filter out through the rest of the galaxy and form a ring, sort of splash-like ring of star formation. And we see ring-type galaxies all over the place. There are many examples of ring galaxies that must have had very, very close encounters with smaller galaxies that are then disrupted. And there's another one, ARP 147, that shows a ring-like structure, as well as another ring, a double ring type structure going through. Starburst galaxies are another classification that we have, and that's what we really are calling these things. And starburst galaxies can be seen by their spectra as well as by their images. And starburst galaxies create huge, huge, huge output, and that enormous, enormous output. What it'll do is it'll create very, very short-lived O and B type stars, which are incredibly hot and luminous, and they make the galaxy extraordinarily bright. And what happens is, though, that these O and B stars make shock waves that cascade through and burn up all of the gas in the galaxy within a few million years, leaving it with some blue patches, but then a bunch of red stars. So effectively, they wipe out all of the gas that's left in there, and the supernovae that are triggered by these O and B stars within a few million years create enormous winds that blow the gas and dust out of the galaxies. And so intense star formation also comes with enormous winds. And this is the antennae, which are a very fast interacting galaxy group. And the core of the antennae shows a vigorous star formation. We can zoom in on this Hubble image and see huge scads of blue-type stars, red regions of star formation, where H2 regions, these pink glowing clouds, where H2 regions indicate hot ionized gas. And then we have extremely turbulent areas where lots of gas and dust are forming many, many, many stars extremely rapidly. And they will form shock waves and supernovae, which will blow the gas out of the entire galaxy very soon. And here we see a region that is coming out of a density wave and forming huge numbers of O and B type stars. And the pink glows, of course, hydrogen. The dark areas are dust, and the glows of the stars are actually tens of thousands of hot O and B type stars, all seen in one galaxy group called the antennae, the core of a pair of interacting galaxies. And here it is also in the ALMA array, which is in microwaves, which will show where a lot more gas and dust are. All right, so another great interacting pair is M81 and M82, and they are a classic interacting pair of galaxies. Sorry about that. They're a classic interacting pair of galaxies, M81 and M82. They're about 12 million light years away. The one on the left is M81, the one on the right is M82, and the one on the left is sometimes called Bode's Nebula. And what we see is that they have recently interacted, and deep imagery also shows that the two of them have a gas streamer between them. But we can see in pink hydrogen off to the right some huge superwinds coming off of M82. And now we're going to focus in on that, and the active galaxy M82 that we just saw in the other image, we just rotated around and zoomed in, and the Hubble Space Telescope took a series of interesting images of it. And that pink glow shows enormous winds coming off of M82, and that is all hydrogen gas. It's being blown out by the star formation and shock waves from previous supernovae in huge numbers, maybe thousands upon thousands of supernovae that are happening all within the last few million years. There was a Type 1a supernova that just occurred a couple of years ago in M82, but that's probably part of the residual of the formation of such things. So keep watching M82. It's actually something you can see with a small telescope in your backyard. It's not that dim. It's actually something you can see very easily with not necessarily binoculars, but definitely an 8-inch scope can definitely pick it out of the sky. So when do galaxies merge, if they collide, and there's enough dissipation of the orbital energy, meaning they don't get flung apart, they don't swing around each other, not going so fast that they just swing by, then eventually the angular momentum gets distributed throughout the entire system and distributed out, and it can lose that orbital energy by dispersing the stars that make up the components. That then makes the gas clouds collide, that forms new stars, and then the entire thing merges into one thing, one big galaxy. So mergers appear to play an incredibly important role in galaxy formation and evolution. In fact, we think that the Milky Way was formed by a construction or a collision of many small little galaxies over its 10 billion year lifespan. And if we think about it, we even now know today that the Milky Way has stellar streams that we talked about in the formation evolution lecture previously. And that is, we would call it galactic cannibalism. So if you have a slow encounter between a large and small galaxy, the smaller one gets torn apart and slowly merges in. So it's not like you get this ring effect, but the little one comes in nice and slow and just gets shredded apart as it comes in slow. So giant ellipticals also may grow by the fact that if you take very large galaxies at very slow motions, then they will actually come together relatively slowly and their cores will stay intact, and that will create a giant elliptical galaxy. So here are some other processes of galaxies that are in the process or the final stages of merging over the next 100 million, 200, 300, 500, 700 million years. Here's another one where we're showing two tidal tails that are coming out and the cores are almost completely merged. And here's one that was showing two spiral galaxies in the process of merging. They're just begun that. I think we showed that one earlier. And here's one from the Swift telescope, and the Swift telescope sees things in ultraviolet. So what we're seeing is when we see, this is a Higgs compact group, one of them, I forget which one, but this particular compact group shows enormous numbers of blue hot stars being formed in the ultraviolet. So we can see that ultraviolet is emitted by O and B type stars, and that's what this mostly picks out. So we're looking at extraordinarily vigorous star formation of young stars. And there's another one, kind of a fuzzy one, I don't know why I threw that in. And we have a ring-type galaxy, a polar ring-type galaxy where you have some sort of a pair of rings pulled together, and this is another Hubble image of a pair of interacting galaxies. And this is a really beautiful one that kind of looks like a pair of owl eyes as they are interacting together, and as they collide together, they're going to distort each other over the next billion years and form one big galaxy. There's another one with a ring-type structure that happened as these two galaxies collided and formed enormous star formation in the ring. There's another one we see off to the side, and some other tiny galaxies all around it. There's a good one that's another ARP interacting galaxy, and so on, and so on, and so on. Part of the reason I'm showing you all these things is because there's a visual vocabulary that comes with astronomy. And the visual vocabulary is so exotic. These pictures could be hung in museums. And in fact, look at this one. This is absolutely gorgeous. Most of the stars, the points, are actually stars of the Milky Way. But we're seeing a pair of interacting galaxies far, far, far in the distance, millions of tens or 20, many tens of millions of light years away. But the stars in the Milky Way are in front of it, and they're only hundreds to thousands of light years away. There's another one, and they're very fascinating things, but also look at the distant ones in the background. When we said that galaxies make up most of the universe, we really do mean that. And so we see that these objects, they're not little galaxies, they're far galaxies that look little. And that's what's interesting about these clear sky ones that are looking up away from the plane of the Milky Way. You see interactions no matter where you look. In fact, peculiar bright galaxies are happening all over the place. this visual vocabulary serves to show you how many things are in the sky and what we can see, and that galaxy collisions are extraordinarily common. And as they occur throughout the history of the cosmos, they build up larger and larger and larger galaxies until we get to things like Milky Ways and so forth. And this is an enormous study that can be done of many galaxies. There are hundreds of millions of galaxies in the cosmos. And as we look out in that, we see huge numbers of them floating around. And wow. But we talked originally about the collision between Milky Way and Andromeda. Right now we know the Milky Way is approaching us at about 120 kilometers per second. And so in about 3 or 4 billion years, the Milky Way and Andromeda are going to collide. And they're going to tidally distort and merge after about 1 billion or so years. And the giant elliptical that should remain will be called Milkomeda. John Dubinsky has a really great metamorphosis that shows this, and it's a wonderful image. I invite you to go check out his website. But I'm going to actually go with the Hubble Space Telescope group that showed exactly how we know this. And we look at the Andromeda Galaxy, and if you look at the edge of the Andromeda, way away from the distant, from the bright core, but way out in the outer reaches, many of the stars that are in the tiny area have a significant amount of proper motion. There's proper motion to them. There's a Doppler shift to these stars that are in this field. So many of the stars in the highlighted area are actually part of the Andromeda Galaxy, not part of our Milky Way. So if we zoom in and look, we can see there's some background objects too, but inside of this study, there are about 10,000 stars from the Andromeda Galaxy. And inside that one little field, there are over 200 distant background galaxies. So if you go hunting, you can find them literally everywhere. And that target field, by comparison, is just about the same size as one of the large mare on the moon. So the moon itself would cover up hundreds of thousands of galaxies every night as it passes through across the sky. All right, so how do they do this? Well, over time, they took a series of observations to see how these things had moved. And so there was some motion of them with Doppler shift, as well as a proper motion, meaning a motion across the sky. And all you have to do is and if it's a fast enough motion, meaning, well, if you're coming 120 kilometers per second, you should see something. And so it's just separated by about a decade or so, 5 to 10 years. You should see some motion of the Andromeda stars relative to the 200 distant background galaxies, because they're going to be fixed. They're not moving anywhere. Or they are moving, but they're so far away that their motions are incredibly tiny compared to the stars in front of them. And the stars in front of them should have some uniform motion. And we're just trying to measure that uniform motion. And as a result of that measurement, it was discovered that the Andromeda Galaxy was moving approximately 120 kilometers per second towards us, and we will have an encounter with it in about 3 billion years. And so the group made an interesting video to kind of show you the encounter as it will occur in the distant future. The Triangulum Galaxy is a satellite galaxy to the Milky Way and Andromeda, and eventually will end up being a satellite galaxy to Milkomeda. And what's fascinating is there is the encounter that we saw that's very similar to the encounters that we saw in many other things. So Milky Way and Andromeda will take over 1 billion years. Look at the time frame that's occurring. It's already 500 million years to go through after the first encounter. And now it's 1 billion years later where the two cores get close, another 500 million years just for them to merge completely. And notice they went from kind of blue to now yellow, as all the stars were burned out that were young and hot, and were left with only the red dwarf type stars in copious amounts. And so after about 7 billion years, well after the sun has died out and become a white dwarf, Milky Way and Andromeda will have collided together and formed one huge giant elliptical galaxy. And so this is some of the things that if Earth were to have survived, this might be the view that we would see. Here is the view from the present day with the Andromeda Galaxy very far in the distance, with our Milky Way in the foreground. And then in about 2 billion years, the Andromeda Galaxy will be enormous. It'll be much larger than the moon in the sky, it will be quite a picture in 2 billion years. In about 4 billion years, it will span most of the night sky. And when the Andromeda rises in the sky, it will be an astonishing view. And very soon thereafter, the tidal distortion will be occurring. There will be huge amounts of star formation as the Milky Way itself gets distorted. Orion nebulas will blossom in the sky, and there will be numerous supernovae to keep everybody distracted. And then when we look at in about 4 billion years, there will be so much star formation that people will be able to read by the numerous supernovae that are occurring in the sky, whose light will last for months. And so there will be a strange element of lack of night due to all of the bright stars in the sky. After about 4 billion years, the Andromeda Galaxy will have passed by, and we'll see an enormous, a tidally distorted Milky Way, all messed up, with Andromeda not looking half as beautiful as it did. That gray just looks kind of old. And then finally, about 5 billion years ago, 5 billion years from today, the cores will get closer and closer together, and eventually in about 8 billion years, or 7 or 8 billion years, there will be a giant elliptical galaxy. There will be no more Orion nebulas, they will be gone. There will be no more tarantula nebulas, they will be gone. They will all be gone in a huge burst of star formation with no gas or dust, but just this yellow glow of billions upon billions of stars in the sky. And that's the future for the view of the Andromeda Galaxy. And this came from NASA and the Hubble Space Telescope, and a group with LeVay and Vandermeer and Hallis and Mellinger over at NASA at Space Telescope. So just go take a look at those wonderful videos that are on that. I provided a link there at the bottom. And here's some interesting review questions for you to go over. And if you want to have some fun and try to see what you've learned. And we'll see you next time.